Hi, and welcome to a lesson about arc length and surface area. In order to make the process of finding arc length pretty simple, I'd like to show you where the process comes from. Back in Calculus 1, you learned how to find the area under a curve by using approximating rectangles. And as you added more and more approximating rectangles, you got a better and better idea of what the area was that was under the curve. If I want to estimate the length of a curve, I can use a similar process. But instead of rectangles, I can use line segments. Take, for example, this blue polynomial curve that you see here. I can keep adding in segments, each of which gets smaller and smaller as we progress on. The more segments I add, the better I seem to fit the polynomial curve. Shown here are 8 segments, and as you can see, as I add more and more and more segments, they become smaller, and they start to take the shape of the curve. As I keep dragging my slider, you can see that even after about 23, 24 segments, you can barely tell them apart. The idea of adding up all of these segments leads us to a formula that we can use to determine the arc length of any curve. And the theorem goes as follows. Assume that you want to find the arc length of some function f of x. Its first derivative f prime exists, and is continuous on AB. The arc length of the function can be determined by integrating 1 plus the function's derivative squared, all under square root, dx, from a to b, and the interval will be specified for you. I'm going to walk you through a few examples where we'll apply the formula. First, we're going to take a look at y equals 1/12 x cubed plus x to the negative first on the interval from 1 to 2. In order to give you an idea of what exactly it is that we're finding the arc length of, I'm going to pull up an applet that will show you exactly what the region looks like. Our curve is right here in red, and it's a very tiny curve from x equals 1 to x equals 2. In this case, the a would represent the 1 and b would represent the 2. As you add in more and more segments, you can barely differentiate between the red part and the blue part. In the beginning, you could see just one segment which connects the endpoints, and as we add more and more and more, you can barely tell them apart. Our arc length estimate seems to be at about 1.72-ish. Let's take a look at exactly where that comes from. Finding the arc length is relatively straightforward with the formula. Some obstacles that we may be faced with later on are what happens if we have complicated functions underneath the square root. How do we handle those? We might need to revert to trig substitutions. But for now, with the polynomial, it won't be too bad. If you take your function 1/12 x cubed plus x to the negative first, the first thing you want to do is find the derivative of the function. In this situation, the first derivative of the function is x squared over 4. Let's just insert a minus here. The first derivative of the function is x squared over 4 minus x to the negative 2. We use the power rule separately on each term, this term and this term. Once you find the first derivative, the rest is smooth sailing. What you then want to do is square your first derivative and add 1 to it, which will be shown in the next step. Squaring the first derivative usually involves FOILing. So in this situation, you're going to take x squared over 4 minus x to the negative 2, and you're going to square it out by writing it out twice, and then add 1 to it. The interesting thing that happens is when you add the constant terms together, the negative 1/2 and the positive 1, it turns into positive half, which can be refactored pretty easily. As a matter of fact, it looks just like the original problem squared, but with the sign change in the middle. Instead of having a minus, we now have a plus. And that seems to be a common thing for this type of problem, that once we add 1 to it, the factoring barely changes from the original. It's especially important that we try and at least write it as a squared quantity, because after all, we will be taking the square root of the quantity as shown in the formula right over here. We will be taking the square root of it in order to find the antiderivative and then plug the bounds in to find the total. So having a square is a nice thing. We'll proceed now with the actual plugging back in and integration process. Once you find the derivative, square it and add 1. You plug it right back in to your integral. To your square root rather. So you plug it right back in here. We replace the red underlined part with what we just calculated. Right, that goes right under the square root. We take its square root, note the absolute value, but it's actually not going to matter since we have positive bounds, and we also have 2 positive quantities. So in the next step we can just disregard that and start the integration process. Okay, and we find the antiderivative each term. For the x squared over 4, that becomes x cubed over 12, and for the 1 over x squared, that becomes negative 1 over x using the power rule. Remember, you want to rewrite that as x to the negative 2. The last part, you want to plug your bounds in, plug the 2 in, we'll get 8 over 12 minus 1 over 2. Then we'll plug in the 1. When I plug in the 1, I get 1 over 12 minus 1. It's tough writing with these markers. And last, you just add up your like terms. 8 over 12 minus 1 over 12 is 7 over 12. And then we have a negative 1. That'll turn to a positive 1. I'll try and keep common denominators. So I'll change the 1 into 12 over 12. And last, I'll subtract the 1/2 over here. 1/2 we'll take as a unsimplified fraction 6 over 12. And we got our final answer of 13 over 12. Which matches our arc length approximation from earlier in the applet. Approximately 1.17266,192. Right, so that's a pretty straightforward application of the arc length formula. Next, we'll consider another example. This time we'll switch it up and add in some logarithms and an upper bound of 2e just to see how that works. So like before, we're going to use the same exact formula, and the steps will be find the first derivative, then we're going to square it, add 1 to the total, see if we can rewrite it as quantity squared, find the square root, and then see if we can integrate the resulting expression. So first, we'll calculate the derivative of the function, and that's by using the power rule for the first term, x over 2, and for the second term, simply take the ln x portion of it. Its derivative is 1 over x, multiply it by 1/2, and we have 1 over 2x. That's our first derivative. Next, in order to apply the formula correctly, we're going to square our first derivative and add 1 to it. So next, we will do exactly that. We will take our answer from before, our derivative. We're going to square it out, which will involve FOILing, and then we'll add the 1 to it. And once that's all done, notice here, this is the result of having a negative 1/2 appear from the FOILing, and then adding the 1 in the front. So we did 2 steps in 1 here. The x squared over 4 you can see is coming from x over 2 squared, and the 1 over 4x squared is coming from 1 over 2x squared. The negative 1/2 that was here came from multiplying the outer and the inner terms together. And just as in the last example, you notice we can factor this very conveniently to be x over 2 plus 1 over 2x squared. Much like in the last example, where all we had to do was take the opposite sign of what we started with. The contents are identical, except we have a different sign. So that works out very conveniently for us. Once we know that, we can take this expression and put it right back under the square root. Like before, we're substituting our answer right under here. So here it is. Take the square root, and we have our expression 1 to 2e of the absolute value of x over 2 plus 1 over 2x. Now, we will also note that on this interval, this is a positive function, x over 2 plus 1 over 2x. Any value plugged in between 1 and 2e will result in a positive output, so the absolute value bars are not necessary in this situation. And our final step, we will take this expression and find each antiderivative, then evaluate the definite integral. The x over 2, by using the power rule, add 1 to the power, divide by 2, that's x squared over 4. And the 1 over 2x, think of it as, when you're doing the antiderivative, think of it as 1 over 2 times 1 over x. And the antiderivative becomes more clear. The 1 over x goes back to an ln x, and the half can stay out in the front. Plug in your values, 2e squared over 4. The 4's will cancel out, so you get e squared. The ln of 2e, that we can also evaluate. We can split that up into ln2 plus ln e by log expansion properties, multiply them each by a half, and then subtract. When you plug the 1 in, you have a fourth, and then over here, the natural log of 1 is 0, so we never quite see that term, so we just get the fourth. And here's your final answer, e squared plus ln2 over 2 plus 1/4. One interesting thing about the arclane formula is that sometimes you might not be able to find the derivative, square it, plug it back in, and evaluate the resulting integram. In some cases, you might need to use the numerical integration process, trapezoidal rule, Simpson's rule, midpoint rule, etc. Let's take, for example, this function right here, 1 over x. Let's say we want to find the arclane from x equals 1 to x equals 2 using Simpson's rule. Just like before, we are going to try and attempt to use the arclane formula. We'll calculate the first derivative, which is negative x to negative 2. We will plug that in, square it, and add 1. So our negative 1 over x squared derivative, that turns into the 1 over x to the 4th. Then we add our 1 to it. Alright, then we want to square it. That's how we got this term, and add 1. Now the issue is, if you throw this under the square root in order to use the arclane formula, you get stuck. We're not going to be able to do anything with this. So instead, we'll use Simpson's rule. To use Simpson's rule, we need to calculate b minus a over n, the width of the interval. We have 8 approximations, that's what this stands for over here, and we will need to calculate the value of the function at various places. I have that work listed right down here. Okay, so on a preliminary basis, we need to first find the width of each interval approximation. So we have 2 minus 1, that's our b minus a. Those are given to us over 8. That's our 1/8. And then we want to count from the starting value to the ending value by an 8. So we start at x equals 1, and we keep adding an 8. Notice these are simplified down a little bit. You might want to do 9/8, 10/8, 11/8, 12/8, 13/8, 14/8, and then reduce them. We keep adding an 8 all the way till the end, and then plug everything into Simpson's rule. Remember, with Simpson's rule, we alternate between 4's and 2's up until the very end. And I started just jotting down a couple of them here for the approximation. Whoops. Didn't mean to go down that low. For the approximation, you take b minus a over n, divide it by 3, to be continued.